Hello, class. This will be the recorded lecture for the start of the applications for exponential functions. And the first one deals with money. So these will be some financial modeling. This is section 6.7 in our book. We're not going to do all the models that are in there, but what I decided to pick are probably the most important ones. So we're going to focus on interest rate models and how they are modeled using exponential functions. So before we do that, though, what we're going to do here is introduce a couple terms and what we would call simple interest. And that is an exponential function. And when we get to what we call compounded interest, that's when the exponential functions kick in. So here's a couple definitions. First of all, interest and principal. So the principal is the amount of money you either deposit, say, into a bank account or you borrow to buy something, like a car loan or a house loan or a credit card loan. Interest is the amount of money that you end up paying on that principal for either lending money, which you end up paying, if you end up borrowing money, which you end up paying, or if you give money to the bank, they'll actually pay you interest to allow them to keep that money. And there's two kinds of interest. One is simple and one is compounding. And the difference between the two is the simple interest, the interest only occurs on the original principal, where compounding occurs not only on the original principal, but the previous interest that was earned before. And you'll see that the compounding effect has either a huge benefit if you're a saver or a huge not so good benefit if you borrow a lot of money. So the first thing we always want to start with is the simple interest formula. And so you could see that is the interest I is equal to the principal P, interest rate R. Now, when we talk about interest rate, we use percentages, but when you plug them into the equation, you always want to plug them in as a decimal. So for example, a 6% interest rate would be 0.06 in this equation. And time is defined in years. And so if you are looking for 2 years, you would plug in 2. If you're looking for 1 year, you'd plug in 1. If you're looking for 6 months, you plug in 1/2. So that's how those numbers get calculated. So I'm just going to show you a couple of these. Hopefully they're reasonably straightforward. But say like you deposited $2,000 in a savings account with an interest rate of 6%. Find the interest at the end of 1 year. So basically what we do here is we plug in 2,000, see the interest rate 0.06, convert it from percentage to decimal, and time is 1 year. And so at the end of the first year, you would have $120. So hopefully pretty straightforward. Here's an example of one where you have $1,800, 8% interest, in 2 years. So again, plugging in the appropriate numbers, at the end of 2 years, you would have an interest of $288. And that would work in the opposite. Say like you were paying back a loan of $1,800 and it was a simple interest. What happens after 2 years? You would have to pay back $288. So before we introduce the idea of compounding and what that kind of equation looks like, I always like to kind of just walk through a nice little example. So let me walk through this example here. So say like you had $100, right? And just to make the math easy, let's take an interest rate of 10%, which would be 0.1. So let's see what happens when you do simple interest. And I'm just going to do a couple years, but I have a 5-year table I'll show you with regards to this. And so in this case, This is the year, okay? And let's see here. Let me get this a little bit nicer. Okay. And then this would be the interest. And then this would be the balance. And so in the first calculation at 0 years, obviously you have 0 interest and you start with $100. So what happens in year 1? Well, year 1 would be 100 times 0.1, and that would equal $10. And so at year 1, you would have $110. What happens at year 2? Well, year 2, same thing, right? Original principal times 0.1. You add another $100. And I think you could see the pattern. So say like you went all the way down to 5, you would see at the end of 5 years, you would have $150. So what happens in the compounding case? Well, here we'll call it compounding. And so in the compounding case, what ends up happening is, let me generate this again. So we start here, and this would be the interest calculation. And this would be your balance. So at year 0, you have no interest, and you stick in that $100 and see what happens. So what happens at year 1? Well, year 1, exactly the same. You have 100 times 0.1, and that gives you $10. So at the end of year 1, you have $110. But here's the compounding effect. What happens at year 2? Well, at year 2, you end up getting interest on the $110 now. So if you multiply that by 0.1, you see now you have $11 of interest. So you add that here and you get 110 plus 11 is $121. And so if you kept going down to year 5, you would end up with $161.05. So you can see that you have $11.05 more interest at the end of 5 years. And the longer that you keep the money in there, the more the compounding actually has significant impact on the overall principal you would have at the end. And so here's the table that I was talking about. And this idea of compounding versus simple interest. And so you can see a much nicer detailed table that I tried to do on the whiteboard. And so let me introduce you a couple of these formulas. First one is compounding interest rate. And this one is used for all the calculations where this compounding thing is the n in the equation. And so A would be the amount of money you have after T years, and P is our principal. And then R will be our interest rate, N is compounding. And the way that it works is the number of times you compound per year. And T again is years. And so if you have a fraction of a year, make sure you put in a fraction for that as well. So what do we mean by this compounding? Well, if we think about it, there are a few typical compounding. One is yearly, and that would imply n equals 1. So every year, like we did in our table, it would go into the account, and then next year you would get interest on that. Sometimes it's semi-annually, which means twice a year, and so n would be 2. One that happens quite a bit is quarterly. Stock market, everything is quarterly, and so that would be 4, and so 4 times a year. Monthly is another one, all right? That might be the most popular one. I could ask the question, a show of hands, how many people have credit cards, right? And so every month you get a statement, and if you don't pay it off, then that's how they'll charge you interest, and here's the n equals 12. If you have a home loan, a car loan, typically all loans are get paid every month. You end up doing a payment. So that's a very popular one as well. There's something called daily, which is not so popular. And then there's one called continuous. And again, not as popular as it used to be, but we have a different equation for that. So these are the ones that we're going to be focusing on the most. And like I said, yearly, quarterly, monthly are the main values, especially monthly if you're doing a loan. And so let's do an example. So let's see what we got here. So let me clear this off here and generate our equation up here. So again, our equation is A equals P 1 plus R over NT. Okay, so the problem in hand here is that, say like you have an interest rate of 2%. So then R would be 0.02. And it's compounded quarterly. Like I said, is a very, whoops, let's try that again. Quarterly. So in that case, N would be 4. And we're going to start with $1,000. And let's see what happens after, say, 1 year. So how would we set this up? Well, we're looking for the total amount we'd have after 1 year. So our p-value is the initial principal of $1,000. And then we have 1 plus R is 0.02. N is 4. And then 4 times T, which is 1. So you have to get used to using your calculator. I'll show you the process that I use. So the first thing that I do is I'll do what's inside the parentheses. So that would be 0.02 and then 4 divide. And so that would be 0.005, and you add 1 to that, this would be 1.005. And then it would be 4 times 1 is 4. And so now you have to take that to the 4th power. And so if you do that, you'll end up with 1,000. And then when you do that, it would be 1.02. 015. And so when then you multiply that together, you would get $1,020.15. So typical process is that you could type this if you have a fancy calculator, right? Or do what's inside the parentheses first, take it to the power, and then multiply right there at the end. And so one last example is to talk about continuous. And it's crazy, but this is really, is that if you start making n bigger and bigger and bigger, you would find that we end up with that whole crazy equation being reduced to the natural base. And that was that limit as n went to infinity, as we talked about initially. And it's crazy how often this happens in real world applications. But here is the compounding continuous case. It's A equals P E to the RT, which is much easier. And so in this case, if it's compounded continuously, we revert to this equation. And so let's take a look at this. And so I'm just going to use the slide for this one, but say like we have a principal of 1,000, interest rate of 10%, which would be awesome. And what happens after 1 year compounded continuously? So you just plug them in. So it'd be 1,000 e to the 0.1 times 1. And so let me just pull up the whiteboard here and make sure that everybody knows how to plug these in. So again, we have a e to the p, or p e to the rt. And so in this case, we had 1,000 for p, r is 0.1, and t equals 1, and it's compounded continuously. So a would be 1,000 e to the 0.1 times 1. And so again, getting out your calculator, you would see that you would have a little over 110. It's 110, 5.17. So you could see if it was simple interest rate, it would be 110, right? 0.1 times 1,000 is 10, or 0.1 times 1,000 is 100, right? And if you add that to your principal, you would get $1,100, right? And this is a little bit bigger than $1,100. So there is a benefit to the compounding, even here continuously, even after 1 year, you got a little more than $5 extra. So it's quite a big benefit, and especially time on your side. The longer you leave the money in, the bigger the continuous aspect of your money growing will be. And that's why they always say, invest early. So that ends the first of the 2 recorded lectures for financial modeling.